This video will explain the Pythagorean theorem and some of its uses. So here I have a right triangle between these squares. And I've sort of removed this triangle here so we can get a closer look at it. A and B represent the legs of this right triangle, and C is the hypotenuse. The hypotenuse is always located across from the 90-degree angle, and it is always the longest side of a right triangle. What the Pythagorean theorem states is that the sum of the squares of the legs is equal to the square of the hypotenuse, and that's written here. So the leg squared plus another leg squared is equal to the hypotenuse squared. A and B here, if this one were B and this one were A, that wouldn't really matter. So this diagram here sort of visually represents what the Pythagorean theorem is stating. A squared is the area of this green square. B squared is the area of the blue squared, and C squared is the area of the red square. This leg squared plus this leg squared is equal to my hypotenuse squared. My green square plus my blue square is going to have the same area as my red square. The most common use of the Pythagorean theorem is to solve for side lengths. You'll be given two and you'll need to find the third. It doesn't matter whether the variable is the hypotenuse or a leg, we can still find it. So in this first example, how could I set this up? So I have legs and a hypotenuse. I would always start by labeling my legs and my hypotenuse as A, B, and C, just so I'm very clear whether it's going to equal the variable or the variable is going to be added to another number. You'll see as we continue. So now it's really clear that if I'm going to have A squared plus B squared equals C squared, how this would translate. And again, if this were A and this were B, that wouldn't matter. All that's important is that the C is across from the 90-degree angle. I also labeled it C here just to help, but oftentimes you'll see it labeled as X. So this labeling is a helpful tool. From here, A squared would be 5 squared plus 12 squared is going to be equal to C squared. 5 squared is 25. 12 squared is 144 is equal to C squared. 25 plus 144 is 169 is equal to C squared. Now, I'm not interested in C squared. Again, C squared would be the sum of the area of a square coming off of here. That's not what I want. I just want C. To get C by itself, I need to take the square root of both sides. The square root of 169 is 13, and the square root of C squared is C. So I've just solved for C. This is 13. Let's try this one. This one's a little bit different. So here I have, well, again, let's label. I have A, and I'm going to choose to label that one A because there's an A there, but I could have labeled this A, B, and C. You'll notice here that it's not going to be what's on the other side of the equal sign, that's my variable. And a lot of people make common mistakes here. When I set this one up, I'm going to have to set this up as A squared plus B squared, which is 15 squared, is going to be equal to 17 squared. So now I can't square these in my head. So what can I do? I would set up A squared is equal to 17 squared minus 15 squared. I just brought the 15 squared over to the right side by using subtraction. From here, you could use a calculator to solve this. Another sort of useful tool that you guys are just going to have to memorize are the Pythagorean triples. And you'll notice that 5, 12, and 13, that came out pretty nice. It was pretty lucky that I ended up with a number that has whose square root is a whole number, and I didn't get some messy fraction. These are called Pythagorean triples, and there's a whole bunch of them, and mathematical way to find them, but really it's just these first four that you're probably going to need to memorize and see on the test. 3, 4, 5 is the most common. After that, we have 5, 12, 13. This one we just solved. 8, 15, 17. So using 8, 15, 17, if I have a 15 and a 17, I can just go ahead. I don't even need to set this up. I know A is going to be equal to 8. If you type that into your calculator as you were watching, hopefully you got that a was equal to 8. And 7, 24, 25. So these are really ugly numbers to find the squares of, especially if it's on a non-calculator section. But if you have this memorized, it's really easy to spot Pythagorean triples. Most common is you will see the 3, 4, 5 or some version of it. When I say some version, I mean that you might see, what if I multiply them all by 3? Some sort of multiple. So I might see 9, 12, and I might ask for this one. Now, if I can spot that I can reduce these here to 3 and 4, then I can have, all right, this is 5. Now I just need to multiply by my scale factor of 3 to get this to be 15. That's how I could find that right there. So again, working with scale factor. If I have a 3, 4, 5 and a 6, 8, 10, those two triangles are similar. Their side lengths are proportional and their angles are congruent. So I don't need to worry about testing to make sure it's similar. I can know it's the triple even if it's a multiple. 3, 4, 5, again, the most common one, and you'll definitely see multiples of it in many, many problems. The other application of Pythagorean theorem is to test to see if a triangle is a right triangle. Because the formula a squared plus b squared equals c squared does not work for acute triangles or obtuse triangles. It only works for right triangles. So that's one way we can test it. So if I wanted to test that if it's a right triangle, I need to, again, pick what's A, what's B, what's C. This one's not that tricky. We aren't given a right angle, so it might be difficult at first to identify. C is always going to be your biggest number, always. So always make your biggest number C, and then the other ones don't matter. So I'll make that one B, this one A. Let's do the same thing down here. I know 12 has got to be my C. 6 is my, let's make that A, and this is B. So now when I set this up, I can say a squared plus b squared equals c squared. A squared is 10 squared plus b squared, which is 24 squared, is equal to 26 squared. And this equal sign is what I'm trying to prove. Is that true? So I'll put a question mark by it because we don't know that those are equal. You'd have to put those into your calculator to find out. Another thing you can spot. If this triangle is a right triangle, then all triangles with sides proportional to this one will also be right triangles because they'll be similar triangles. So their angles will have to be the same. So if you have numbers like these and you think, oh, maybe I can reduce. Reduce before you test this because you might end up with a triple. For example, I spot that these are all even numbers. So I can divide each one by 2. That would give me down here, I would have 5. Here I would have 12, and here I would have 13. 5, 12, 13 is a Pythagorean triple that we saw in the last slide. So I don't need to do this math to go to my calculator, especially if it's on the non-calculator section. Yes, this is a right triangle because that's a Pythagorean theorem. Let's try that down here. Again, I could set this up the long way. I could say 6 squared plus 8 squared equals 12 squared. And again, I'm going to circle the equal sign and put a question mark by it because that's what we're trying to test. I'm not sure that that's true. So just because I put the equal sign there, we're trying to see if that's the case. I also notice here I can reduce, again, by 2. So let's see. Let's get the 6. That would become 3. This would become a 4. Now, I know the Pythagorean triple is 3, 4, 5. So if this number, when I divide it by 2, is not 5, it's not going to be a triple. And of course, 12 divided by 2 is 6. 3, 4, 6 is not a Pythagorean triple. This is not a right triangle. So that's one way that you can test that. In fact, if the hypotenuse is bigger, this is actually going to end up being an obtuse angle. So this is going to be greater than 90. If this were a number smaller than 5, let's say this were 4, then this would be an acute angle, and this would be an acute triangle. So that's also an interesting way to test what kind of triangle it is. Usually you're just going to be asked, is it a right triangle? But if it's bigger than what it has to be a right triangle, then it'll be an obtuse, because this angle needs to get bigger to fit in 6 when if it's a 90 degrees, it's only 5. If it's smaller, then this angle, at 90 degrees it would be 5, so if it's 4, it's got to be a little bit less. It's an acute triangle. So we can use the Pythagorean theorem to figure out what types of triangles they are without knowing any of the angle measures.